analysis. So I've made that material, the lecture material, available on D2L now. There's a PowerPoint presentation that we're going to start with on Wednesday. So those slides are printed for you to view in advance if you'd like. And then there's also a handout that is the assigned reading for this lecture. So I'll point that out to you if I remember to at the end of the day today. I think I've got them just ready to go on my iPad here. And then, and then we'll see what questions you have. I did post a homework assignment, homework 5. It's due 2 weeks from today. So originally I was going to have it due next Friday, but as I was looking at the schedule, I think the following Monday will work out better anyway, because next week you have the career fair, so I'd like to kind of keep that open. And then that'll give you also some space around the exam. So, but it is going to be your first homework assignment on finite element analysis, so I wouldn't wait until, a couple days before it's due to start it. Definitely give yourself time to get going on it and get your questions answered. So I still recommend that you start it early, and get set up and think through it. So homework 4 is due tonight. Any questions on that? Okay. All right, good deal. And remember, the exam covers material through homework 4. So none of the finite element analysis will be on the exam, but everything before that is. All right, any other questions before we get going? All right, good deal. So quick recap. All right, we were talking about how to apply finite element analysis to trusses. And so even though trusses consist of single degree of freedom elements in their local context, right, because they're just axial only members, because they are arranged in a way where those axial directions vary within the system, we need to define 2 degrees of freedom for the system, right? So we use our global X and global Y, and then we had to go through this process of transforming the geometry of the displacements and forces. So we break them down into global X, global Y components for our analysis of the system. And so that's what we went through last time, and we landed on this equation here, all right? So this is our global element stiffness equation, which relates global forces to global displacements. And that just means it's the components in the global X and global Y direction of the axial force and axial displacement. So here is the formula for that global stiffness matrix. And we defined A and B in terms of the angle theta, which measures the orientation of the element, right? And we said that theta is always going to be measured positive counterclockwise at node I from global to local. So the expanded form of our global element stiffness equation is shown down at the bottom of this page. And this right here can be your starting point for any given truss element, right? So, but you have to calculate this for every single truss element separately, right? But the nice thing is we can kind of skip all of this, right? Starting from the local and going through all that, and just use this formula. So we'll summarize the overall process, and then have a few more comments on it, and then roll into an example. So first, we want to determine the local stiffness, the transformation matrix, and then the global stiffness for each element. But as I said just now, right, really you can just start with the global stiffness matrix since we have that equation on the previous page. All right, so in order to do that, of course, right, it's assumed that you know the angle theta and you also know the relative AE over L property for the element that you're writing the global element stiffness matrix equation for. Once you have Kg for each element, then you can start applying the overlay. So that's assembling all of the elements together to represent the entire system. And again, that's in terms of global coordinates. Then once you have your overlay, you solve for the unknown global displacements and reactions. So from there, our process is just the same as what we would have done previously with demonstrating with the single axis axial force system, right? So we would identify the boundary conditions, eliminate the columns that are associated with zero displacements, find that first partition has to be square, solve for the unknown displacements, and then once you've got those unknown displacements, plug that into the second partition equation and solve for the unknown forces. Once you have found the global displacements and reactions, you can take those and plug them into the individual member local relationships, right? So you can use the displacement transformation equation, right? This was the equation 2 from the previous couple pages. To solve for the local displacements, just plug in your xg. And then once you have the local displacements, you can plug them into the first equation, which was the local element stiffness equation, to get those internal forces. All right, so these would be your solving for axial deformations. And this would be solving for the internal member forces. Right, and those would be either in tension or compression. So I'll just point out a few other things, right? So global displacements, that's going to come from the first partition. And then your reactions will come from the second partition. So down below, I've got a list of some notations, and this is set up originally written to be consistent with the previous couple pages and then also with the example that we're going to look at now. But I have a couple notes here, right? Instead of using x1g, x2g, like I described last time, where an odd number represents displacement in global x and an even number represents displacement in global y, it might be better, or I don't know, it might make more sense to you to just say x and then 1 or whatever the node number is and y1, all right? So here n would be the node number instead of playing with the odd even thing. I think personally that this approach makes more sense. I prefer it. I'll just note here where n is node number. And then there's an example on the last page of the handout that uses this notation. And also the little example or below uses that approach as well. All right, so here, just demonstrating using an element between nodes M and N, right? So the angle theta, remember, is measured positive counterclockwise at node I, which just means the lower numbered node, so in this case it would be node M, from the global x, which is always the horizontal, positive to the right, to the local x. So the local x is always going to be measured from the lower numbered node towards the higher numbered node, right? So in this case, that's your local x direction. So this theta would be measured like that, or you could say, you could identify what this angle is and just call it negative, whatever the value is, right? So if this, yeah, well, you get that. All right, so then your global element stiffness equation for element Mn would be shown here, right? And again, when you overlay the matrices, it's important to map the correct values to the correct location within the global matrix. So I always like to keep them in order, so consistent order in the individual element matrices would just be the lower numbered node in the first 2 rows and columns and the higher numbered node in the last 2 rows and columns. And then in the global overlay, right, keep it in order too. So then it helps a little bit, right? It's not going to be as straightforward as it will be with beams when we get into that, but I'll just note, all right, so we've got your the node M displacements, right? So the columns associated with node M in the individual element would go in the columns associated with node M in the global matrix. So if we had, all right, our node M columns and rows identified, that would go right in there. And then your node N values, all right, would go there. And then you would map these guys here and so on. All right, so this one, because node M and M are adjacent numbers, it's pretty much the same thing as just taking this matrix and dropping it in the same 4x4 chunk of the overlay. But some of your elements will be spread out, right? So if there was an element connecting node 2 to node N, then that element would drop in here, right? Part of it would go here, part of it would go here, and then part of it would go here. Okay. So on the diagonals, the diagonal 2x2s, that's where you're going to have an overlap, right, or values added together from different elements. Any off-diagonal 2x2 will not have any overlap, so it'll just come from one element. We'll look at that too at the last example with more numbers and stuff, but just as a heads up. That's what that mapping will look like. All right, so, one other comment I want to make before we move on here. The size of the overlay, right? We have 2 degrees of freedom, so it's going to be 2 times however many nodes we have. All right, so that is going to be the same essentially for a truss as 2J. All right, since joints and nodes are interchangeable. All right, so moving on to this example, we have a 2-bar axial force system. All right, so this is a very basic truss. Pin supports at nodes 1 and 3, applied load at node 2, which is where the 2 members connect. So first thing we want to do is identify the local x-axes for each member, right? So we make sure that we got our orientations correct and the angles correct, and then identify the angles and write the global element stiffness matrices for each element. So for member 1, 2, right, x will be measured positive from node 1 to node 2. At node element 2, 3, right, x will be measured positive from node 2 to node 3. So our angles then for node 1, we want to measure it positive counterclockwise from the global x to the local x, or we can just say it's negative 45. All right, so that's written down here. And then theta 23 is measured from global x to local x, so that's going to be positive 45. So that's down here. So for element 1, 2, A and B will both have a magnitude of 1 over the square root of 2, but B is going to be negative, right? And in some cases, right, if you mess this up, if you mess up the sign, sometimes it won't make a difference in terms of your global results. It may or may not, right? But when you go back to your local element, your local element stiffness matrices, and you try to use those global results to calculate your local forces and displacements, if you had this wrong, then that direction could get messed up. So you might get correct global results but incorrect local results, if that makes sense. So just keep that in mind. All right, so, and remember we had A was equal to cosine theta and B equal to sine theta. When you have the 45-degree angles, right, it makes things easy, and it's easy to forget which one was which, but I'll just write it down there for your notes. All right, so this here is your kg for element 1, 2. And as you can see, right, I've just sketched each element with the proper orientation showing the angle, and sketched on there the degrees of freedom. So that would be your x3g, x4g, and so on, the forces as well, right? Just sketching them, assuming the positive direction for everything. So what I'm going to do now is label the columns and rows according to what node they're associated with. So here we have the node 1 rows, node 2 rows. Here's the node 1 columns. And the node 2 columns. All right, and if you like, I like, again, to label the columns according to what displacement they're associated with. So then for element 2, 3, we have node 2 columns and rows, and node 3 columns and rows. And this, of course, is your global stiffness matrix for node element 2, 3. All right, so I'm just going to highlight then where the overlay is going to come from, right? So we are going to look at node 2 because that's the node that has more than one member associated with it. So the values that are in the node 2 columns and rows from each element will get summed together in the overlay, which is on the next page. So I'm going to go ahead and label our overlay columns. All right, so we've got our node 1, node 2, and node 3. So here at node 2 is where that overlay occurs. Now at this point, we can start to apply our boundary conditions, right? So at node 1, it's pinned, so that means we know that node isn't moving, right? It's not going anywhere. X1 and X2G are both 0. Same at node 3, right? Both displacements at node 3 are 0. So on the other side, then, we have the forces that we know at node 2. And in the x direction, global x, which is F3G, that's equal to positive P. And there's no force applied in the y direction, so F4G is 0. So that means, right, and it's just rewritten below for convenience. So that means we can eliminate the first 2 columns and the last 2 columns from our analysis, because those values are just going to get multiplied by 0 in the matrix equation. And then we identify our first partition, which is going to have the rows with known forces. So that's going to be rows 3 and 4. All right, and those get multiplied by X3G and X4G. And that means our second partition will consist of the remaining rows. All right, so we'll piece together rows 1, 2, 5, and 6 for the second partition. Any questions so far? Yeah?
Can I ask what AE over L is?
That's the stiffness, that represents the stiffness of the axial member, right? So remember last week when we talked about, when we introduced this method and said we were looking at springs first, and then I was like, okay, now if we consider an axial bar, that we replace K with AE over L. Yeah, that's where that comes from. And if we go back to, right, thinking about the mechanics relationship, you remember the equation PL over AE is equal to delta, right? Yeah.
On the exam, are we expected to be writing out each of these steps and all these matrices?
Potentially, yeah. So not on exam 1, right? But on future exam, I'll talk more about, you know, what you might be able to, what you might be expected to do on the exam. But you may be asked to show the whole process. Most likely what I will do and what I've done in the past is, for example, I may provide you with the overlaid matrix and say, take it from here. So, yeah. Yeah, but they're also, I've also asked, you know, questions before where, you know, you're maybe asked to assemble the overlay, right? So yeah, I most likely will break the problem up a bit so that it's doable in the time period that you have in the exam. Any other questions? Okay. All right, so next page, we have the first partition written out, all right? And once you take the inverse of that stiffness matrix, which includes the AE over L term, right? So we've got now L over AE from the inverse. Pre-multiply both sides by that inverse. We solve for those unknown displacements, and the results are in terms of the applied load and the stiffness. So we see then that in this case, right, the node 2 will displace in the positive direction. So I'm just going to sketch that actually right here. So this means node 2 will move in the positive direction, right, by some amount, but it's not going to have any vertical displacement. So it's not going to move down or up. And then, right, we can imagine what that's going to do to, the bars that are attached to node 2. All right, so we can expect one to shorten and one to lengthen. All right, so now that we have those displacements, we go back and identify our second partition, which I already highlighted that in blue. All right, so that's associated with the rows that have unknown forces, because now we want to solve for those reactions. And we just plug in the x3g, x4g values, all right, because we're just using the columns associated with the displacements that are non-zero. All right, now technically in this second partition, you could go ahead and you could take the all 6 columns, right? You could go ahead and do that because the second partition doesn't have to be square for you to solve it, right? But if you do that, it's just kind of extra work writing it all out because they're just going to be multiplied by 0. They won't contribute to the solution. All right, so what I want to show here. All right, we're going to take this, plug it in right there, and then solve for the reaction forces. So at node 1, just sketching our results, right? F1g was the horizontal, and that's a negative direction, magnitude p over 2. F2g was the vertical, that's the positive direction, magnitude p over 2. And then at node 3, all right, we had also negative direction horizontally, magnitude p over 2, and then negative direction vertically, magnitude p over 2. Summary shown on the entire structure, right, showing the applied force and all the reactions that we found. Eyeballing it, we can see quickly that sum of forces in x and y are equal to 0. What I haven't shown here, but what you should always also check for a truss, is sum of moments about a point. So I will write that check out here. Right? You can pick any point. Usually it's convenient to pick a point on the structure. I'm going to pick node 1. So we can do that by saying, all right, we've got our applied load P at node 2 times the moment arm to node 1. Well, what do we know about geometry? We know that 2 elements have the same length, right? And we know that they're angled at 45 degrees. So this distance will be L over the square root of 2. This distance will be L over the square root of 2. And this distance will be L over the square root of 2. So our moment arm from the applied load is going to be L divided by the square root of 2. And then we have, since we're summing moments about node 1, the only other force that causes a moment is the vertical reaction at node 3. So that's going to be minus P over 2 times 2L divided by the square root of 2. And that does check out, right? So it's important to always check all 3. That was actually a common mistake on homework 3 for the first problem when you were asked to verify the equilibrium with one load case. There were several folks who checked sum of forces in x and y and said, oh, good to go, but didn't check sum of moments about a point, right? But it's important to do that because if you can't show that sum of moments about a point is equal to 0, that means that it's unstable with regards to rigid body rotation. So sum of forces in X and Y alone is not sufficient to verify that. All right, so a couple more comments, right? It makes no difference using the finite element solution if the problem is determinate or indeterminate. In fact, indeterminate problems become easier to solve because the more indeterminate it is, the more zero displacements you have, right? Because the more supports you have. So that whittles down the size of your first partition, makes it a little bit easier to solve that part, and then you can go from there. So yeah, so that speaks to the second column, right? The fewer number of unknown displacements need to be calculated, the more indeterminate it is. All right, so any questions before we continue? All right, so at this point I've demonstrated how to get all of the global results, right? We have our global displacement of node 2 and the global reaction forces. But we might want to know how much member 2-3 is shortening and how much member 1-2 is lengthening, right? So for that, we want the local results. So that's continued on the next page here. So here, we have to go element by element, and we're going to take the global displacements to find the local displacements. So we'll start with the global displacements, right? The results from that first partition. Once we've found the local displacements, we plug them into the local element stiffness equation to get the internal forces. So we'll start with member 1-2, right? It's written out here. I think these notes are pretty complete. So I'll just make some notes on here, all right? So we have the transformation matrix for element 1-2 written out, and this is where that sign is important of the theta, right? So this is where that can really make a difference in your results. Again, it may or may not affect your global results, but it'll definitely affect your local results. Applying, right, x1 and x2 are equal to 0, so that means we can ignore the first two columns in that equation, and then we get, okay, so I didn't include the results in your skeleton notes, so we'll write that out. So our results for x1 and x2, we get, where do I have them written down? Here they are. My notes are a little bit split up on different pages, so we get x1 is equal to 0, and x2 is equal to square root of 2 over 2 times PL over AE. All right, and just a gut check, right? The units of those symbols should check out to be equivalent to units of length, and they are. Now once you have, and by the way, these x1, x2, right, that's the same as the lowercase delta 1, delta 2 that we looked at last time, right? So you can use either notation, that's fine. All right, so we get x1 equals 0, that checks out, right, with the pin support. So node 1 isn't moving axially. Node 2, we got a positive value, right, for our result. That makes sense with the positive x direction and the fact that we intuitively know that this member should be in tension and lengthening, right? So we have a positive displacement at node 2, and then so that checks out that our member is going to be in tension. And then plugging in those values to our F equals KX, right? Now we have our internal axial force. And these should always be the same magnitude, right? Because your K matrix is going to be assembled of 1s and negative 1s. So these two member end forces should be the same magnitude and opposite directions. Interpreting that to our sign convention for the local axis, right? At node 1, we have F1 is square root of 2 over 2p. And at node 2, in the opposite direction, right, positive direction, square root of 2 over 2p. Now for a member, right, this is consistent with tension. It gets confusing because we talked about previously with trusses, when you show directions, you show them how they're acting on the joints. So these directions would indicate compression in that context. But here we are obtaining member results, not joint results, okay? For element 2, 3, similar approach, right? Now we know, plug in our values for x3g, which was PL over AE. Is that what that was? Yep, x3g was PL over AE. All these are zeros. All right, and by the way, above here, same thing, PL over AE, 0. Solving then, we get x2 is going to be square root of 2 over 2 times PL over AE, and x3 is 0. So again, that makes sense. x3 is not moving, x2 is. But here we got a positive result for x2, right? So that means it's going to move in the positive direction. So positive does not necessarily equate to tension in these results, right? So that's the thing I want to point out here. In this case, our positive x direction is from node 2 to node 3. That means the member is going to shorten, right? So it's in compression. That checks out. Force results, once we plug that x2, x3 into our F equals kx, we get F1, or well, this is written down wrong. All right, so correction to the notes. This should be F2 and F3. So F2 is square root of 2 over 2 times P, and F3 is negative square root of 2 over 2 times P. So again, interpreting that at node 2, whoops, we have the positive direction, and at node 3, we have the negative direction, right, which is consistent with compression. So then at the bottom of the page here is just a comment on that convention, right? Our results that we get for member forces and displacements are shown as they act on the member, not on the joint. So you can think about this, right, if we want to expand it, right? The joint can be here, right, where the force on the joint would be acting in the opposite direction. Questions? Okay. So in the homework 5, that's again due in 2 weeks, you're going to be asked to go through that process with a different truss. And you're also going to be asked to, at some point, plug in values and calculate actual numbers in inches. But it's important to not plug in any values until after you've obtained the finite element solution. So this example kind of continues on to expand, adding a third bar to the system. And I'm just going to highlight the few additions to this and show you how that's going to change the overall stiffness matrix in the solution. So here we would add two forces and two displacements. Right, at node 4. Also, this example is adding a vertical force at node 2. So that's another addition to this. So all we would need to do to add this member would be write the global element stiffness equation for the new member, 2, 4. All right, here theta is measured from global x to local x. Local x would be measured positive from node 2 to node 4. So theta is equal to 90. That means A is 0 and B is 1. So your global matrix for this one is a bunch of zeros and ones. We'll identify the values that are going to be added to the overlaid portion, which are going to be the node 2 values. And then the rest, all right, I'm just going to highlight and identify. This will go into the node 2 columns and the node 4 rows. Or I got that reversed. Node 2 rows and the node 4 column. All right. These will go into the node 4 row, node 2 column. And then these will go into the node 4 row and node 4 column. All right, but again, the overlay occurs at node 2. So on the next page, I've got that expanded overlaid matrix. Right, here's the overlay where those values are added in. So that's your node 2 columns and rows. Here are the node 4 columns and rows, which are the new pieces of that matrix. And that's where those values from up here got dropped in. All right, so you can see how this matrix is spread out in the global matrix. So now still have a 2 by 2 first partition, right? It's just got some modifications to it. Solve for those unknown displacements. Now they're in terms of P1 and P2 since we have an extra force that we didn't have before. Plug those results into the second partition. And then you have 6 reactions that you're solving for. So, and then by the way, right, since all of these 6 displacements are zeros, that means we are eliminating 6 columns from our analysis. All right, so the node 4 columns we didn't even really have to put in, like. Yeah.
Where do all those 1/2s come from again?
So they came from the first 2 bars, right? So that's, we're taking this matrix, right? Because it's the same problem, we just added a bar here, right? So that's where the 1/2s came from. Yeah. All right. So a quick summary of this, and then I'll have a few comments after that. So quick summary of our axial force system applied to trusses. So this is comparing, right, the single axis or local element for axial force systems. Number of degrees of freedom is 1. For trusses, we have 2 degrees of freedom, right? Because we're working in terms of global displacements. For the single axis axial force system, we know either the axial internal force or the axial deformation. For a truss, At each node, we know either global Fx or x displacement, and we know either global Fy or the y displacement. Size of the stiffness matrix for single axis or local is going to be 2 by 2. Let's see. Yeah, so I'm going to clarify here what I mean by the lowercase k and the uppercase k in this. So the lowercase would be your element matrix. The uppercase k would be the system, right, or the overlay. All right, so for a truss, the element stiffness matrix would be a 4 by 4. All right, and that's in terms of global displacements and forces. And then for a whole system, right, it depends on how many nodes you have. So for a single axis, it's n by n. For a truss, it's 2n by 2n. Questions? All right. So we just have a few minutes left. Since we didn't get around to talking about the exam today, I'll spend some time on Wednesday to do that for you. I want to say for the rest of this, so this is the other example that I mentioned earlier, right, where you have a full truss system, and you can see here we're just looking at 3 elements. That would be the elements that connect at node 2. So we have those individual global element matrices written out, and then you can see how they map to the overlaid system, right? And wherever there are zeros in a 2 by 2, that means there's no node there's no element connecting the nodes associated with that column and that row. So there's no element connecting node 4 and node 2, right, which is correct. Node 2 is over here, node 4 is over here. All right, so that's one thing to keep in mind. Another thing, right, I already mentioned it, but the overlay occurs always on the diagonals. So that's going to look like that, where the overlay is. So I can spend a few minutes talking about that later as in the context of a recap or summary. But what I do want to point out is this is where you're going to find the homework problem. All right, so the homework problem is going to refer to problem 16.6 in your notes. That's this one. So this is the truss you're going to analyze in your homework. And then if you haven't yet, check out the exam info that I posted on D2L. So it's a new folder called exam info or exam stuff or something along those lines. And this goes through, right, the logistics, what you can expect. So format will be 2 to 3 working problems plus 5 to 10 short answer or conceptual questions. Those could be multiple choice or, maybe short answer like draw the deflected shape of this beam or, something like that. And then I go through the different topics, right, break down some of the key items and have a few comments in there, but make sure that you review the lecture notes and homework and assigned readings as you go through and study. Okay. And on Wednesday, I'll see if you have any questions for me on specific topics. And then we'll do visual analysis stuff. Okay. All right. Very good. Well, thank you all for your attention. I'll see you on Wednesday.